Okay, this is exam 3 for Physics 101, fall 2017. This first question is about conservation of energy. I have a bug that has 0.0032 mass, kilograms of mass, and it's 0.4 meters above the ground initially, and when he lands there, he has a speed of 1 meter per second. So I want to know, what is his speed down here? All right, I know that up here he has both kinetic energy and potential energy, and that all of that energy will go down here only into kinetic energy. So I'm going to set those two energies equal. That is 1/2 mv squared plus mgh equals 1/2 mvf squared. Notice that my masses cancel, even though I'm given it, I don't need it. And let's see, I can put in some values here. 1/2 of 1 squared, that's just going to be 1/2, plus 10 times 0.4, that's equal to 4. That's 1/2 vf squared. So that's 4.59 times 2 is 9 is equal to vf squared, so vf is equal to 3. 10 kilogram, excuse me, yeah. So a 10 kilogram kid comes down a slide. The slide is 2 meters high and 4 meters long, so it looks like this. 4 meters here, 2 meters here. The slide has a frictional force of 5 newtons, so I have a force of 5 newtons that acts along that slide. How fast the kid when he reaches the bottom? Well, at the top, he only has potential energy. At the bottom, he only has kinetic energy, but he has lost a certain amount of work. And so the amount of kinetic energy that it has at the bottom is equal to the potential energy minus the work that has been done by that force due to friction, and then that's going to equal his kinetic energy. So mgh equals, or excuse me, minus the frictional force times the distance is equal to 1/2 mv squared. And I have all these quantities here. I just need to solve now for what is v. So mgh, that's 10 kilograms. That's his mass, 10 meters per second squared. The height is 2 meters. Minus the force, which is 5 newtons, that's the frictional force, times the distance down the slide, that's the distance over which the force acts, is equal to 1/2 of his mass, that's going to be 5 kilograms, times v squared. So that's 100, 200, 180, that's 200 minus 20 divided by 5 equals v squared. That's 36 equals v squared, and then the square root of both sides is 6. Child slides down a playground slide. If the slide is 4 meters high and the child has a mass of 20 kilograms, how much potential energy is at the top of the slide? Well, potential energy is mgh, so that's 20 times 10, and he's 4 meters, so that's 200, that's 800 joules. Which of these statements is true? Gravity is a conservative force. Non-conservative forces lose energy. That's correct, like friction. Conservative forces are path independent, not path dependent. And conservative forces require contact between two surfaces. In fact, if you have contact, that is not a conservative force. So 1 and 2 only. So 4 is E. By what factor does kinetic energy of a car change if its velocity is doubled? Remember, kinetic energy is 1/2 mv squared. If I double this quantity, I'm going to quadruple the kinetic energy, so by a factor of 4. Which of these expressions represent power? Power is energy over time, or work over time. That's just energy. That's work times time. That's kinetic energy. This is work. This is work over time. Consider this figure. 3 blocks of mass m slide down 3 inclined planes, each at height h. They have kinetic friction. That's really all that you need to know. Which has the most energy at the bottom of the inclined plane? This is like the slide problem we worked a few problems ago. So the one that loses the least energy is this one, because that distance is the shortest. So therefore that one is going to have the most energy because friction is acted over a shorter distance. How does the work required to stretch a spring 6 centimeters compare to the work required to stretch it 2 centimeters? Well, I'm stretching it 3 times as far, and the potential energy of a spring is 1/2 kx squared. So if I triple that, then I get 9 times the elastic potential energy. So I'm required to have 9 times as much work to stretch it this 6 centimeters. So number 8 is D. How much work does it take to make a 20 kilogram wagon speed up from 2 to 4 meters per second? All right, the work is equal to our change in kinetic energy, and so that's going to be 1/2 mvf squared, that's my final kinetic energy, minus 1/2 mvi squared. So a half of m is half of 20 times vf, which is 4 squared minus 2 squared. Notice I factored out the 1/2 m because it was common. 16, 10, 120. So D is number 9. You increase the energy of an object by 200 joules by pushing on force F. So the work that I've done is 200 joules. I've done this over a distance of 4 meters, and I want to know what is the force. So 200 is equal to the force times 4. So it's going to be 50 is 10B. You move 3 identical blocks along a frictionless inclined plane. Rank the situations below according to the work done by the forces. Well, I have a big force here acting over a small distance. And I have a small force here acting over a big distance. I know that work is equal to force times distance. And then I have a medium force acting over a medium distance. And so it's not clear right away by how much is the force different from the displacement to be able to rank the works. So let's think about this in a different way. What is the change in potential energy going from here up to here for all 3 blocks? The change in potential energy for each is the same. They all experience the same potential energy. So therefore, the forces all do the same work. So D is 11. How much force would be needed to cause a 20 kilogram meters per second change in the momentum of an object if the force acted for 4 seconds? So I have a change in momentum equal to positive 20. And the time is 4 seconds. Remember by Newton's second law that force is equal to delta P over delta T. I'm looking for the force, so that's 20 divided by 4 or 5 newtons. It's a useful thing when I'm looking at collisions. When does the net force on an object increase? Well, look here again. If delta P decreases, the force decreases. If delta T increases, the force also decreases. So I know it can't be either of those. However, if delta T goes down, F goes up. So C is the right answer. What is the final velocity of the 2 kilogram ball? I have 2 situations here, the initial and the final, and I need to calculate the initial and final momenta. So momentum, remember, is mass times velocity. So I start with the initial, that is 1 kilogram times positive 3 meters per second, plus 2 kilograms times negative 4 because it's going to the left, is equal to 1 kilogram times negative 1, that's for this particle, plus 2 kilograms times, well, what is VF for that particle? And, you know, right away I should be able to tell that, well, no, never mind. I was going to say that I could tell right away that this thing has to be going to the right, but that's not entirely clear because this one has a big mass and a big speed and a negative momentum, so the net momentum may be to the right. Let's just see. We're not really sure. So 3 minus 8 equals negative 1 plus 2 VF. And I solve this for VF. I have negative 5 plus 1 equals 2 VF, negative 4 over 2, negative 2 equals our VF. So it's going to be 2 meters per second to the left. You see, I was wrong actually. It is actually going to the left. This guy, which has the big mass and the big speed, dominates the momentum and overwhelms us when they both start moving off to the left. So what's that? Number 14 is A. Okay, a person with mass 60 kilograms is standing still, and he throws an object with mass 12 kilograms. So this person is here, they have this object, they're standing still. Actually, the ball is over here. And then this is the initial momentum here is equal to 0 because nobody's moving. That looks like a cheerleader, doesn't it? All right, but now throws this object in this distance, in that direction rather, and the person starts going off at 2 meters per second. I know that he throws the object because the object has to have an equal but opposite momentum as the person. So I have the initial momentum is 0 equals the final momentum. That's going to first be of the ball or the object. That's 12 kilograms times VF of that object plus the mass of the person, which is 60 kilograms times 2 meters per second. So VF is negative 10. D is 15. Cart has a mass of 20 kilograms, is traveling to the right at 12 meters per second. You drop a mound of trash onto it from the cart from above. The trash has a mass of 10 kilograms. What is the new speed of the cart? So initially, this is traveling at 12 meters per second with 20 kilograms. That's initial. You'll notice the initial momentum is 240 kilogram meters per second. That's 20 times 12. Final, I drop this stuff here. So now it has 30 kilograms. And I want to know what is the speed. Well, PI is equal to PF. 20 times 12 equals 30 times VF. What is VF? That's 240 divided by 30. It's equal to 8 meters per second. Notice it slows down. So A, 16. Crane drops a 0.3 kilogram steel ball on a steel plate. Okay. I like to draw pictures, so let's see here. This is 0.3 kilograms. The speed just before impact is 4.8 meters per second. But notice that it's dropped, so we'll say that's negative. And then the thing rebounds. It bounces up again at 3.2 meters per second. So that's positive. And I want to know, this is the V initial, this is V final. I want to know what is the magnitude of the average force. Well, by Newton's second law, F equals delta P over delta T. I can find that force. It's going to be the change in momentum. That's M times VF minus VI over delta T. That's 0.3 times VF is 3.2 minus negative 4.8 divided by 0.03. And that works out to be 80. Uranium nucleus is at rest and undergoes fission and splits into two fragments, one heavy and one light. Which of these is true? The heavier fragment has more momentum. I know it has 0 momentum here. Here, each of these have to have equal and opposite momentum. They do not, however, have the same speed. This one is slow, and this one is fast because they have different masses. They have the same momentum, but different masses. The lighter fragment has more momentum than the heavier fragment? No. But the lighter fragment does have the same momentum, so D is 18. Calculate the angular speed, that's omega, of a 0.2 meter radius car tire when the car travels at 10 meters per second. This is going to be V. The car is traveling at 10 meters per second, that's the speed, but that's also the linear speed of the tire. So if I think about the tire with the road, which way is it rotating? It's rotating in this direction. The linear speed, the tangential speed at any point on that tire is going to equal to the speed of the car. So all I'm looking at here is V equals omega R. 10 equals omega times 0.2, and 10 divided by 0.2 is equal to 50 radians per second. How many radians are in 270 degrees? You want to do a battery stretch, sorry. So don't forget your unit circle. 0, pi over 2, pi, 3 pi over 2, and then 2 pi. So A is the right answer, 20. If you were uncertain about this, you could always do a unit conversion. Do 270 degrees times in 2 pi radians, there are 360 degrees. And then you would get a decimal number that would be about 4.5, which is 3.3 pi over 2. Isn't that right? 1.5 of 3. Yeah, about 4.5, which is equivalent to 3 pi over 2. So the easier way is just to know your unit circle. Calculate the centripetal force exerted on a 1,500 kilogram car that rounds a 200 meter radius curve at 15 meters per second. Okay, remember this centripetal force is provided by the frictional force, so that's not really terribly important here. It does exist though, and that centripetal force is equal to the mass times the centripetal acceleration, or mv squared over r. That's going to be 1,500 times 15 squared divided by 200. 15 cubed over 2. Which is D. Tornado is 40 meters in diameter. Carries 100 meters per second wind. Actually, hold on. Let me stop here for just a second. Okay, yeah, there was an error here. I'm sorry. I'll fix this for your test. This should be the radius. Okay, a tornado is 40 meters in radius and carries 100 meters per second wind. This is R, this is V. We know its angular velocity, that's omega. So V is equal to omega R. It's like we did before. Omega is V over R, which is 100 over 40. It's 2.5. Oh, but 2.5 isn't the answer because that's in radians per second. I need to convert this to revolutions per second. And 2 pi radians, that's 1 revolution, and that's equal to 0.4. So C is the right answer for 22. When a fan is switched on, it achieves an angular acceleration of 30 radians per second squared. What is its angular velocity after a time of 4 seconds? So omega is equal to omega naught plus alpha t. Omega naught is equal to 0 because it's just switched on. So this is equal to 0 plus 30 times 4, 120. Potter's wheel moves from rest to an angular speed of 2 revolutions per second in t equals 3 seconds. What is the angular acceleration? Now notice this is in revolutions per second, but this is too. If you wanted to convert units, you could to radians per second, but then you'd have to convert them back to revolutions. So I'm going to keep everything in revolutions. This is one of those cases where when you're doing your kinematics, it doesn't matter if you have radians or revolutions. So what am I looking for? The acceleration. So is this omega equals omega naught plus alpha t. That's going to be 2 revolutions per second equals 0 plus alpha times 3 seconds. And so alpha is 2/3 revolutions per second squared. Is C for number 24. Okay, if it has speed omega, omega equals alpha t. I know that because it's initially at rest, so omega naught is 0. What if I double the time, then I double omega? So A is the right answer. And then this fan is spinning and it's speeding up. So this is a negative omega. Get rid of these. And if it's speeding up, that means that the acceleration is also negative, is in the same direction. So D is the right answer. And here, what's my favorite part of the day? Filling out paperwork. I love to fill out paperwork. It's like the highlight of my day. Dealing with the administration. Listen, I like the dean and the provost and all those people, but I love to deal with them. Writing grant proposals, yeah, I love that too. But going to class, that's my favorite part of the day. All right, because we get to talk about physics and I get to see you people. So anyway, that's the end. Let's see, there's all the solutions. Notice that there were a lot of OpenStax questions on this. I had warned y'all about that.